In this presentation, we're going to discuss electrostatics. So when we talk about electricity, we're talking about a form of energy that results from the existence of charged particles. And these electrical charges can be actually either moving or static, not moving. When the charges are moving, we call that an electric current, which we'll discuss in the next presentation. But right now we're going to talk about what happens when those charges are at rest and they don't move. And sometimes we call this static electricity. And in static electricity, the charges can get greater or smaller on an object, but they don't really move. The first law of electrostatics talks about how the charges either attract or repel each other. And as we talked about earlier, positive charges or like charges, like these two positive charges we see on the left here, will repel each other. Also, we can have like charges that are two negatives, and again, these two negatives are going to repel each other as well. But if we have a positive and negative charge, well, now these attract each other. And to talk about why this happens, let's go back and review some of our atomic structure. And we talked about how our atoms are composed of protons, electrons, and neutrons. Protons, which have a positive electric charge, so it's going to repel other positives and attract negative charges. Our electrons, which have a negative electric charge, so they're going to repel other negative charges and attract positive charges. And then our neutrons, which have a neutral electric charge, they're neither positive nor negative. So our atoms have their nucleus, which is positively charged because our nucleus has those protons and neutrons in them. And then our atoms also is surrounded by a cloud of negatively charged electrons. And each of the electrons in any atom has the same quantity of negative charge and the same mass. So there's not really any difference in the electron on this side of the atom and the electron over on this side of the atom. They're going to have the same quantity of negative charge and they're going to have the same mass. In the nucleus where our protons and neutrons are, when we look at the protons, they're about 1800 times more massive than the electrons. So we can see why most of the mass of an atom is in its nucleus. And each proton has amount of positive charge equal to the negative charge of one of the electrons of that atom. Neutrons are even slightly more massive than protons, but they have no net charge. So they don't really affect the electrical forces. And atoms usually have as many electrons as they do protons. So most atoms have a zero net charge because the negative charge of their electrons cancels out the positive charge of their protons. The only particles that are free to move are the electrons. And so the electrons carrying that negative charge in a conductor can move either from one shell to another in the same atom or from one atom to another. The protons and neutrons, however, are very tightly bound inside the nucleus of the atom. So the protons and neutrons, they're not going to go anywhere. It's very difficult to move them out of the atom. When we have an atom that, say, loses one of its electrons, then we have what we call a positive ion. And remember, ions are just atoms that have more or less electrons than is usual for that type of atom. So if it loses an electron, it has a positive net charge, and it's going to be a positive ion. If an atom gains an electron, well, now it's going to have a negative net charge, and we're going to call it a negative ion. The electrons in an atom, the ones in the inner shell, the innermost ones, are very strongly attracted to the nucleus because, of course, that nucleus has the opposite positive charge. The outermost shells, the electrons here are attracted more loosely because that charge is going to disperse over distance. And so these and the outermost shell can be more easily dislodged. When we have two atoms that come in close proximity to each other, the balance of attractive and repelling forces might not be equal. So these atoms may have opposite charges and they may attract each other and form a molecule. All of the chemical bonding forces that hold atoms together to make molecules are electrical in nature. They are based on those opposing charges of atoms. It's important to remember that in any charging process, we're not creating or destroying electrons, we're just transferring these. So there is a conservation of charge, just like we've talked about in earlier units, conservation of momentum or conservation of energy or conservation of heat. Same thing with charge. We're not creating or destroying any electrons, they're just moving from one material to another. In the 18th century, there was a scientist named Charles Coulomb who was investigating charges, and he created the inverse square law of charges. And this says that the force between two charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. And that sounds pretty familiar. It's almost like the Newton's law of gravitation, right? So if we have two charged objects and we double the distance between them, the inverse square says the force is going to be only a quarter of the strength that it was before we moved the objects. If we have the distance between two charged objects, now the force is going to have 4 times as strong an effect. And this is the second law of electrostatics. And again, it's similar to Newton's law of gravitation for masses, but it's important to realize that in electrostatics, we can either have repulsion or attraction. Gravity only has that attractive effect. But with electrostatics, we can either have a force that's pulling the objects together, an attractive force, or we can have, if they're both the same charge, we can have a repulsive effect where the objects are pushing each other themselves away from each other. We also measure charge in coulombs, and 1 coulomb is the charge held by 6.25 times 10 to the 18th power electrons. And you can see that's a whole lot of electrons if we write out our number in conventional numbers. When we talk about charges, we can also talk about conductors or insulators, just like we talked about conductors or insulators in heat. And a conductor, when we talk about charges, is any substance that allows a charge to flow through it. And basically what this means is one or more of the electrons in the outer shell of those atoms are not particularly tightly bound to the nuclei, but are free to wander in the material. And when we look at conductors of charges, we see that most of our metals, such as silver, copper, and aluminum, are great conductors of charges. Also, some nonmetals, such as graphite, which is what makes up the lead in your pencils, and things like salt solutions are good conductors. And you might notice that some of these things that are good conductors of charges are also good conductors of heat because it's the same principle. These electrons are allowed to kind of wander and disperse that energy. Insulators, on the other hand, just like an insulator in thermodynamics resist the flow of heat, insulators also resist the flow of electrical charges. And that's because in these particular materials, the electrons are tightly bound. They belong to one particular atom, and so they're not free to wander about and disperse that energy. So things like glass, wood, ceramic, paper, most plastics are insulators. They resist the flow of electrical charges. And we can also see that these substances also resist the flow of heat. There's also some substances that are called semiconductors, and these are substances that behave sometimes as an insulator and then sometimes as a conductor. They're in many cases these substances are insulators when they're in their pure state, but if we add an impurity, which is called chemical doping, then they become a conductor. We can layer some of these semiconductors together to make things like transistors and integrated circuits in our electrical devices. Some substances that are semiconductors will conduct their charge or lose their charge when a certain wavelength of light hits them. For instance, selenium. Selenium is an element that can hold a charge until it is exposed to light. And so selenium is quite often used in photocopiers. In a photocopier, we have a drum that is covered with selenium or some other type of semiconductor. And then when we want to copy a document, we put it on a screen and that document is exposed to light. And on the white parts of the document or the blank page part of the document, the light's reflected back to the drum. Whereas in the parts where there's ink, the ink does not reflect the light. So that light is not reflected in the drum where there's writing or ink on the page. Where the light was reflected and it hits the selenium on the drum, it causes the selenium to release its charge. And then our toner or our ink inside the copier is attracted to those areas that still have a charge that were not exposed to the reflected light. And so the drum makes a copy of whatever was written on the original document onto a blank sheet of paper, and our copy comes out. There's also materials called superconductors that have zero resistance to the flow of a charge. Once we establish a current or a flow of electrons in a superconductor, it'll continue indefinitely. And we don't lose any energy or heat in a superconductor because there's no resistance. We can make a material a superconductor when we cool it below what's called its critical temperature. And when we talk about cooling, we're talking about very, very low temperatures from zero, absolute zero, to 100 Kelvin, which is pretty cold. Among common substances, the highest critical temperature known is about 380, negative 380 degrees Kelvin, which is pretty cold. The highest absolute known critical temperature that we know of is about 203 Kelvin, which is still minus 70 degrees centigrade. And we can get this from taking hydrogen sulfide and put it under extreme pressure, and it becomes a superconductor at that temperature. So we've talked about charges and how does a charge actually get on a substance? And we call this acquisition of a charge charging. And one way we can do this is by either friction and contact. So think about if you have a pet cat and you stroke the cat on a cold winter's day, sometimes you can actually feel uh, a little tingling, or you can even visualize sparks coming from the cat's fur. Or if you shuffle your shoes or socks on a carpet and then touch a metal doorknob. Or in this, we see in this picture, just the friction of rubbing this rubber rod with some rabbit fur, we can create a charge on the rod. And in this particular picture, what's happened is as we rub the fur on the rod, the fur actually gave up some electrons to the rubber. So now the rubber has gained a negative charge, and the fur, because it lost some negative electrons, has gained a positive charge. We can also get charging by induction, and this is when objects aren't really touching each other, but we bring a charged object near a conducting surface, and then in that surface, the electrons can be made to move in response to that charged object. So this happens, say, in thunderstorms when we have charges separating in clouds. Positive charges build up at the top of the cloud, and we have negative charges build up at the bottom of the cloud. And as those negative charges build up in the bottom of the cloud, they create a positive charge on the buildings and structures below. And let's look at a little bit more deeply about how this can actually happen, how this charging by induction can happen. Let's say in A, we have two metal spheres, and these two metal spheres, if we induced a charge in them, would form a single uncharged conductor. And let's say now we bring a negatively charged rod close to these two spheres. We see all the positive charges being attracted to the rod, so they're kind of moving to sphere A. And then the negative charges are repelled by the negatively charged rod, so they'll kind of move to the other side of sphere B. And then as we start separating these spheres, now they're not touching, and we have all the positive charges in sphere A and all the negative charges in sphere B. We have equally and oppositely charged our spheres. This can even happen way down on the atomic level. We can see it happen in individual atoms, and one side of an atom or molecule can actually become more positively or negatively charged than the other side. So, for instance, if we had this atom here in A, the charge is pretty evenly distributed from one side of the atom to the other. But say we brought a negatively charged object over here to the right, now we can see the positive charge is kind of pulled to the right and the negative charge pushed to the left. And now our atom is considered polarized, because if we cut right down the middle of this atom, we would have more positive charge on the right side of the atom and more negative charge on the left side of the atom. So we can see this happening in this picture here. If we have a charged object that is negatively charged brought close to these atoms, the positive part of the atom or molecule is tugged towards the rod, the negatively charged rod. The negative part of the atom or molecule is pushed away from that negatively charged rod. So we can see the atoms or molecules in this substance here. The positive part of the atoms or molecules is pulled to the left towards that negatively charged rod, where the negative part of the atom or molecules is pushed aside. So we can call this substance now, here on the right side of our picture, polarized, because we have the positives towards the left and the negatives towards the right. You can experiment this with little pieces of paper and even a comb. And your comb has a positive charge. The paper is electrically neutral, but yet when we bring that positively charged comb close to the little pieces of paper, the molecules in the paper become polarized. So the negative charges are pulled towards the comb, the positive charges are pushed away. Now, the negative charges are going to be closer in each atom of the paper. The negative charges are going to be closer to the comb than the positive charges. And remember, when we talked about the attraction of charges, the closeness, as the closer the charges get, the stronger they are. So the closeness is going to win here, and the bits of paper will be attracted to the comb and stick to your comb. And you can do this with things like balloons. If you rub an inflated balloon on your hair, it becomes charged. It picks up a negative charge from your hair. And if you go and you place it against a wall, a lot of times the balloon will stick. And this is because the balloon induces an opposite charge on the atoms of the wall. The positive charges are pulled close to the balloon, the negative charge is pushed away. And again, the charge on the balloon is slightly closer to the positive charge in the wall and further away from the negative charges, so closeness wins, and the balloon and the wall are attracted. There's lots of molecules that are electrically polarized in their normal states, which means the distribution of charges in this molecule are not evenly distributed. So there's a little bit of more negative charge on one side of the molecule than on the other side of the molecule. And we can call these molecules electric dipoles because they have two poles. And here we can see a graphic of, say, a water atom. So we have our hydrogen atom that here and our two oxygen atoms here. And the positive charge is pulled towards the oxygen atom, and the negative charge is concentrated in the hydrogen atom. When an item has an electrical charge, the space around it also kind of has a force, and we call this an electrical field. It's almost like an aura that surrounds any type of electrical charge. And this electrical field also obeys the inverse square law. So the closer we have two items, the stronger the field between them is going to be. If we move them further apart, the less strong that field is going to be. And the magnitude of our field is going to be the force per unit of charge of that object. So when we talk about electrical fields, if we have a positive charge, we think of the electrical field as moving in the same direction as the force of that positive charge. So when we draw electrical fields, we draw them as radiating out from a positive charge. We look at the direction of electrical field as moving opposite to the force, though, on a negative charge. So when we draw our negative charges, we show the force lines going to the negative charges. And this can kind of help us understand why like charges repel and opposite charges attract. So in here, we can see that from the positive particle, the electrical field is moving out from the positive particle and to the negative particle. So they attract each other. And this happens whether we have two particles of opposite charges, or we have maybe a plate and a particle of opposite charges, or two plates of opposite charges. It works the same way. But now let's say we have two like charges, two positive charges here. Well, now the force lines are moving away from both particles, and they really can't go to each other because they would want to go to a negative particle. So they push each other away. When we have charged particles, each of these charged particles has what we call electrical potential energy. And this is energy that these charged particles have due to their location in an electrical field. And if we want to move this particle against the electrical field, we have to do work on that particle. It requires work. And you can think of this, let's look at the top picture. If the spring, the coils of the spring push it away from the wall. Okay? If we want to push the spring to the wall, we have to apply force with our hand. Same thing, we have these two positively charged particles. So we know they want to push each other away. So if we want to push this smaller positively charged particle towards the bigger one, we have to do work on that particle. Okay? And think about in this picture here, if we release the force on this small particle, what would happen? Well, again, it would want to be pushed away. Just like if we release the force on the spring would push out. So if we stopped doing work on this particle, it would return back to where it wants to be, back out here. We can kind of compare this to when we talked about potential and kinetic energy dealing with objects. So for instance, over here on the left, we can see that we have an object held up by a rope, and it has potential energy due to its position and the force of gravity acting on it. And then if we cut the rope, that potential energy becomes kinetic energy. Same thing over here on the right. We have our two charged particles, and one is positive, one is negative, so they want to attract each other, but we're doing work to push the positively charged particle away. So we're doing work on it. And it's going to have potential energy due to the fact that we've pushed it against the electrical field. But now if we take away the work we're doing, whatever force we're using to push the particle away, now all of a sudden its potential energy becomes kinetic energy as the particles are pulled together by that electrostatic force. If we have particles and one has twice the charge as another, it's going to take twice the work to push that particle against the electrical field. We calculate the electrical potential energy per unit of charge, per coulomb. And any location, the electrical potential energy per coulomb is the same no matter how much charge we have. So if we have an item with 1 coulomb of charge and then another object with 10 coulombs of charge, well, the item with 10 coulombs of charge is going to have 10 times the electrical potential energy because each coulomb of charge has the same EPE. And we measure electrical potential energy in joules. Now we come to electrical potential, and this is probably one of the more confusing concepts that we're going to talk about here about electricity, because electrical potential and electrical potential energy are not the same thing. Uh, we talked about our electrical potential energy. We measure in joules, and that is basically the energy a particle has because we've done work pushing it against a field. Our electric potential is that electrical potential energy divided by the amount of charge. And electrical potential is measured in volts. And we can say that 1 volt is equal to 1 joule divided by 1 coulomb. And that gives us 1 volt. So if we have two particles, so we have particle 1A up here, it's kind of small and has a small amount of charge. And then we have particle B down here that has twice the charge. Okay, so particle B is going to have twice the electrical potential energy, but it's going to have the same electrical potential that we measure in volts. And you might think, well, how can this be? And remember that our volts, or our electrical potential, is our EPE, or electrical potential energy, divided by the coulombs. So let's say up here, this guy has 5 coulombs. Okay? So he has 5 EPE. So 5 divided by 5 is going to equal 1. His voltage is going to be 1. Down here, let's say this guy has 10 coulombs, and we know the electrical potential energy per coulomb is the same for no matter how many coulombs we have. So that's going to be 10 EPE divided by 10 coulombs, and we get the voltage still equals 1. So you can see, even though these two particles have vastly different charges, they have the same electrical potential in volts. We can have a high voltage with a small amount of charge, which is going to give us some low energy, or we can have high voltage with a large amount of charge, which is lots of energy. So our lady here is holding a balloon, and maybe she charged it like we talked about earlier in the presentation by rubbing it on her hair or whatever. And these balloons can easily have 5,000 volts of electrical potential. Should she be afraid of being electrocuted? Well, not really, because even though the balloon has a high voltage, the charge in this balloon when we charge it is typically only a millionth of a coulomb. So there's not a whole lot of energy there to be moved from one place to the other. We can also use these electrostatic charges to store energy. We can store electrical energy in a common device that's called a capacitor. And we can make a capacitor just by having a pair of conductive plates, and they're separated by a very small distance, but they should not be touching each other. And then if we connect these plates to a charging device such as a battery, electrons are transferred from using the battery as a circuit from one plate to the other. This occurs as the positive battery terminal pulls electrons from the plate connected to it, and then these electrons are kind of pumped through the battery, and then from the negative terminal go to the opposite plate. And now the capacitor plates are going to have equal and opposite charges. The positive plate connected to the positive terminal, and the negative plate connected to the negative terminal. The charging process is complete in this capacitor when the potential difference between the plates equals the potential difference between the battery terminals, which is the battery's voltage. Remember, voltage is electrical potential. The greater the battery voltage and the larger and closer the plates, the greater the charge that we can store. So If you hooked up a 1.5 volt battery to your capacitor, well, you could get 1.5 volts stored. If you hooked up a 9-volt battery to your capacitor, well, you'd get even more voltage stored. The energy stores in the capacitor comes from the work that was done by the battery required to charge it, the work moving those electrons from one place to the other. A common use for capacitors is in defibrillators, and defibrillators use batteries or household current to charge a capacitor, and then when it's activated, the capacitor delivers this charge through pads or paddles to the patient's body, and this can deliver about 4,200 volts or approximately 970 joules of energy to the patient, and this resets the patient's heart and hopefully restores a normal rhythm.